Lesson 1. We are talking about concept of instantaneous rate of change. So rate of change is a big calc topic. You heard it in algebra and pre-calc a little bit, but we really hit on it in calculus here. So as we read here, as students of life and algebra, you've studied many rates of change for different situations. How fast we drive, how our savings grows over time, the rate the world population changes, our growth rate every year, unemployment rates, and so much more. In each of these studies, we can express one variable in terms of another. That is a function, y equals f of x, where y is your function and x is the variable within the function is what we're looking at here. But those are all rates of change. When we talk about how fast you drive, okay, that is a rate of change. Okay, and that is what is changing.
Speed.
Right, but so what is that when we think about the speed you drive? Miles per hour, right? So your miles, your distance is changing over time, right? Over hours. So, okay, velocity. This is a big one in calc. Consider an object that travels in a straight line. The average velocity, so watch, there's some different vocabulary words here. Let me get a color. But right here it talks about the average velocity over some given time interval can be defined as the ratio of change in position to the elapsed time period. So notice right there, ratio, I think fraction, change in position to the elapsed time period. Okay, also referred to as displacement or net change. So when we talk about average velocity, change in position, elapsed time period, I'm going to define that as change in position over change in time. Now, I used a little triangle. Are we familiar with the little triangle? Delta. And it means change, right? The change between two things is that little triangle, which is delta. Think of it as just subtracting two things, right? Okay, so change in position over change in time. When we talk about change in position, that is your change in distance. So we could also do delta D over delta T would be a way that you would see it expressed as well. Okay, so this is average velocity. This is what it's easy to measure. This is what we think of when we think about your speed, when we think about your growth rate, savings, all of those different examples up there. Now, key is when we think about velocity, though, we usually mean instantaneous velocity. Okay, so we're changing that first word, and that makes a difference. Instantaneous velocity indicates the speed and direction of some object at a particular moment, which could be faster or slower than the average velocity. And as we talk about this instantaneous velocity, think about the word. It's velocity at that instant, right? At that, what'd you say, time? Mm-hmm. Yeah, at that point in time, right? So, think about this. Can you explain why we can't define instantaneous velocity as a ratio? Well, but at a time, at a specific time, it would be a certain amount there. Think about how do we find velocity?
You know how it was in another time slot?
Okay.
You can't have an average time.
Okay. So,
zero.
Yeah. So the key is right there. At that instant, more than anything, there's no change in time. If we're talking at one instant, there is no change in time. And change in time is your denominator. And so that would be dividing by 0, which, can we divide by 0? No. So I have written down in my notes the time interval causes division by 0. And there's several issues along the way here, but excited. I have to get my BenQ skills back today. It's been a little rough. You have to get your note-taking skills back, right?
Yeah. I couldn't remember how to spell hasn't this morning. I think we can.
Okay, so time interval causes division by 0. How can you estimate an instantaneous velocity then? If the issue is that we can't divide by 0 because it's just at an instant, at that point in time, how can you estimate instantaneous velocity? We can't have that time period be 0, but we could have it be smaller than 1. Very, very small.
Like 0.001.
Yeah, like 0.00001. You know, like put several zeros in there. Okay, so when we talk about estimating instantaneous velocity, you want to make that time interval very small. Make the time interval very small. Now, I'm going to have to go to the top of the next page for mine because it's right where I broke my page, but let's generalize that big idea with this principle. Average velocity, which is the change in position over change in time, right? Over a very small time interval is very close to instantaneous velocity. It's not exactly instantaneous velocity, but just by doing basic ratios here, we can't find instantaneous velocity. But we can, the smaller and smaller and smaller you make that time interval, we can get closer and closer to instantaneous velocity there. So, key point here is that average velocity over a very small time interval is not exact, but very close to instantaneous velocity. Okay, work to understand the difference between average versus instantaneous. We use both a lot throughout the year. Okay, when we learn derivatives, velocity go a lot with derivatives. I know that word means nothing right now, but it will mean a lot here eventually. Okay, so I suggested you should have your calculators by your side today, right? Let's look at this example. If you climb to the top of the Tower of Pisa and drop a coin to the ground, estimate the instantaneous velocity at 0.7 seconds. Use Galileo's formula, S of t equals 16t squared, to compare the average velocity in feet per second over the time intervals listed in the table below. So what are we going to be doing here? Plugging in numbers? Doing what? How?
Yeah.
Okay, so we have Galileo's formula here, right? And that is average velocity, or that is your S of t, 16t squared. How do we compute average velocity?
What is position over time?
Position over time, right? And if you recall, I know you guys would have talked about velocity. S of t is a position formula.
Okay, that's what I was just
Okay, and that's what I'm trying to think how much we talked about that in pre-calc, and probably not very much, but S of t represents position. Okay, so we're talking here that S of t is your position of, what were we doing, climbing? Oh, and dropping a coin. So that's going to be your position there of the coin is going to be your S of t. So in order to find average velocity, what did it say up here?
Position over time.
Change in position over change in time. They give us a time interval. So what are we doing here? Okay. What were you doing on top?
The SFP consistent position.
A little more specific here. I mean, I somewhat agree with you, but I'm not sure you're 100% there, if that makes any sense.
You have to plug into the 16t squared.
What do we plug into 16t squared?
0.7.
Well, now, okay,
0.7.
are you guys looking that this is the first box we're going to fill in here?
No.
I'm not 100% sure everyone is. So in order to estimate the instantaneous rate of change, we're going to look at the average rate of change. Okay, so in order to do this, change in distance over change in time, right? We have a distance formula, and we have a time interval, yes? So if we're doing change in distance over change in time, change in distance, we're going to what? Not plug in just one value, but
The difference.
plug in both values. It's going to be the difference between the two. Okay, so think of it, think of this as doing S of 0.705 minus S of 0.7 all over 0.705 minus 0.7.
Okay. See, I was like,
Okay.
do we plug that one in?
Yeah, I mean, because we're doing average velocity, and if you recall, that was change in distance over change in time, and S is a position, I guess, is what you usually think of. So that would be your distance.
Could you write it like on top as just S of the difference, just one, or do you have to plug both in?
You'd have to plug them both in.
Okay.
Okay, grab the calculators, do the math. Because here we also need to practice calculator skills, right? I'm debating. Let's see.
Is there like an S for everything?
No, you want guys.
What is S?
It's just
Shoot, basic recalc. S is just that formula right there.
It's like f of x.
Yeah.
So that's the provided formula there. So now one way to do it would be to use your fraction bar, right? At least I would. And then it's what? 16 times 0.705 squared minus 16 times 0.7 squared over 0.705 minus 0.7.
Apparently, I like taking a really long way.
And then I'm just giving you an example of how you could do it. Can you take really long ways and get there? Oh yeah, right? You do you. Because I'm going to show you something else here. Now, this is a pretty easy formula, isn't it? I mean, doing 16t squared, piece of cake to type in every time, over and over and over. What if it's a complicated formula? Do you want to have to type that over and over and over?
No.
Nope, not really. So, you want a plan B?
Mm-hmm.
Now, I haven't practiced this, so you're going to have to, I've got a couple months of summer on me too, so you're going to have to give me a moment.
Can I go crazy?
Yes, of course. And I didn't think to, I thought you were going for a scientific, and I was like, don't go for a scientific.
Oh no.
Pre-calc, we haven't even gotten to those yet. So another option, if you have, and this isn't as important here, but if I go into my y equals, oof, okay, hold on, I gotta change my mode. You want to be in function mode. Okay, now we go to y equals.
Not in that.
I was still in Fuller mode.
Oh, so I'm not the only one.
I'm in like A plus
Okay.
BI and degree.
Yeah, so go to mode
Oh, I'm in
and
Fuller.
pick function.
Should we
I
be in
hope
radiant
that
mode
too.
mess me up on the physics?
I don't think it would have.
Do we want real A plus BI or RE?
Real.
Yes.
Okay, so now, if I go to y equals, I have my y1 through y0, I think technically. But if I go ahead and type in my 16 s squared, realize we don't have an s here, right? We just use x. Where is that? Where did I type that in? I typed that in at y1. Note that in your brain, okay? So now I'm going to get out of here, because I'm not graphing, that's not what I care about. But So now when I go to plug in my next two numbers, again, this isn't a hard formula. So this one's not a great example of it. It's when you have a big, long, nasty formula. This is great. But what I can do here, I'm going to set up my fraction bar again. This time, I'm going to do, what am I doing here? I'm going to do S of 0.7001 minus S of 0.7 over 0.7001 minus 0.7, yes? Well, what I can do here now, I have to think where it is. And I know, okay. So I just got a menu to pop up there if you see. And that is my Alpha F4 menu. Do we all have Alpha menus in here?
What button did you push?
I did Alpha
Okay.
F4, which is your trace button.
Find it?
No.
Hit the alpha button and then hit F4.
F4
Okay,
being the
that's-
trace button up
That's
top.
what I'm trying to find right now.
Up top,
Okay.
top.
Thank you.
Okay, so there it says Y1. So Y1 or Y2 or any of those, where did I type my equation in?
Y1.
Y1. So I'm going to pick Y1 there, and then I'm going to put parentheses after it, kind of like, you know, like it's S of something. That Y1 is taking the position of S. So I typed in then, so this is saying I'm going to evaluate Y1 at 0.7001 minus Y1 again. And this time, what am I evaluating Y1 at? 0.7 over 0.7001 minus 0.7. I just typed in the exact same thing I did up top, obviously with my next set of numbers, but I didn't have to type the formula.
What did I do?
Okay? Again, this was an easy formula. This is kind of overkill here, isn't it? Are they always easy formulas? No. If you've got a big old long nasty equation, there is importance of this. Okay? Keep going.
What did I do?
While I find Sophie's mistake. Oh, you used a, so right, okay. On the bottom, you used negative instead
Oh.
of minus.
Okay.
That took me forever to find too.
Thank you.
I was like, I don't see it. I don't know what you did.
Whoopsies.
I know you did something, obviously, because that
Yeah.
answer was.
Very wrong.
But, okay, find the next two if you haven't already. I'm not going to write the next two out in terms of the work. You can see what to do. You can kind of notice a trend here in terms of what the answers are close to.
Sort of.
Again, it's not a skill you have to use every time, but there are times where you want that skill in your toolbox. Definitely. Okay. You have the next two numbers for me or not quite yet?
Not quite yet.
And this is where you could even go back up and copy and paste
That's what I did.
and just change the numbers within the parentheses, right? I mean, you just have to remember how to insert numbers. Because I think we need another zero there, don't we? Yeah.
Mm-hmm.
And remember, you can go do an insert by doing second and the insert button, which is the same as the delete button.
What'd you get for the last one?
24,000,016.
Really? Okay.
Do I know this one?
Oh, I found my mistake.
Now I have.
There we go.
And can we keep going with this average velocity?
Yeah.
We can keep going, but I think we definitely have enough here to see a trend here, don't we? So what would you say, what is your estimate for the instantaneous rate of change, otherwise known as IROC, at 0.7 seconds?
22.4 per second.
Okay. Okay, and again, that's an estimate, right? But we have enough evidence here, 22.4 feet per second at 7/10 seconds. Okay. Common abbreviations, okay? Calc has certain abbreviations that you can always use. They're kind of universal. IROC, IROC, is going to be instantaneous rate of change. What if I say AROC?
Average rate of change.
Average rate of change, right? Those are universal. That's something you could write on the AP test because that is universal. IROC and AROC, okay? Okay, are we ready? Okay. Study of rate of change. And again, I've said this is kind of a big deal because we'll work with this a lot this year. In that first example, we allowed the time interval to shrink very close to zero. We didn't get to zero, obviously, but so you can say that the average velocity converges to the instantaneous velocity, or that the instantaneous velocity is the limit of the average velocity. And this is where this falls into place, because our first unit in calculus, I think I probably failed to say this, is limits. Okay, if you looked back at the Unit 1 page, it's limits and continuity. We're going to learn everything and anything we can about limits. Okay, this is kind of our introduction with limits in that we also need to talk about velocity throughout the year. Okay, instantaneous velocity is the limit of the average velocity. Okay, so graphical representation here. AROC, okay, average rate of change, or in this case, average speed, is defined by the total distance traveled divided by the elapsed time period. We talked about that on the front page. That was the delta D over delta T. Graphically, the average speed is the slope of the secant line. Do we know what the secant line is?
No, secant sounds really familiar, but I don't think.
Okay, we'll get to that here in a
Because
moment.
again, it's cosine inverse.
Yeah, I know,
So that
but-
would be a mountain to say about it.
I just don't remember it.
Yeah, but we need to think secant in terms of the geometry work.
Oh, absolutely not.
Like when you learned what a tangent line is.
What's tangent line?
That was a
I'm
long
being
time.
so
That was a
serious, I
long
honestly, I don't
time ago.
remember.
Honestly,
Even longer.
That was my
than-
freshman year.
Yeah.
Tangent lines you should know, and we'll get to a tangent line. But we'll talk about secant line here first. So, okay, I'll show you here in a moment. So graphically though, average speed is the slope of the secant line. Analytically, the average speed, which is what we already talked, average rate of change, delta D over delta T. Now, we're going to sketch the secant line. So sketch the secant line through A and B and estimate the average velocity. So your secant line is the line that goes through, basically through the 2 points. Okay, it's going through the curve as opposed to only touching the curve in one spot, which we'll get to in a little bit, and that will be our tangent line. If a line is tangent to a curve, it just touches it in one spot. So I'm going to erase that, but like that's a tangent line. Okay, or that's a tangent line. Well, supposed to be.
So no
Okay.
matter what, like no matter where the two dots are, a secant line just goes through both of those dots.
Right, or it goes through the curve.
Oh, okay.
I guess I need to look up a specific definition of secant line. I just know the idea of it going through the curve. So in this case, and this is where I almost need a ruler, but I can't use a ruler on here, they give us 2 points to use. So we're going to use these. And our secant line, not half bad for freehand, is going to go through those points. Okay. So that is our secant line. And what did we need to find? The slope, right? If it wants us to find the average velocity, well, average rate of change is your average velocity. So delta D over delta T, or in this case, slope of the secant line. Sorry, I was trying to find where it was so I could highlight it. So let's see. A rock, average rate of change, is going to be the slope of the secant line. Our letter that represents slope is M. So that's, I put M for slope, and then I put secant kind of in the subscript. How do we find slope?
Rise up run.
Okay, rise over run.
1/3.
X1 minus X2, Y1 minus Y2.
Stand on your feet, not upside down.
Y1 minus Y2 over X2. X1 minus X2.
Okay, yeah. Change in Y over change in X, right?
Whoopsies.
Or rise over run. In this case, it doesn't really matter. We can probably pretty easily rise over run, yes.
Yeah.
Or if you want to do change in Y over change in X, this is what? The pair 1, 3 and the pair 4, 4. So either way, 4 minus 3 over 4 minus 1, if I've done my math correctly. Okay, so that is our average velocity.
Yes, it's 1/3.
And we don't have, I don't think we have information to have a label on it. Okay, and so it's okay to leave things unlabeled when I don't have anything, do I? Yeah, I don't have any units throughout here. Okay, so that is your idea of average rate of change when looking at a graph. Now, IROC. This is going to be on my next page. Instantaneous rate of change is the speed at a specific instant in time. We already talked about that, where t equals t naught is the limit of the average rates of change. Okay, we talked about instantaneous rate of change being the limit of the average rate of change, right? Now, graphically, the instantaneous speed is the slope of the tangent line at the specific point. So slope of the tangent line. So we're going to have to talk about a tangent line here. Analytically, well, we'll learn more calculus to determine the instantaneous speed analytically. But for right now, we're going to talk about slope of this tangent line. So sketch the tangent line through point C. Can you estimate the instantaneous velocity? So a tangent line does what?
Just touch it.
It touches, it's touch and go. Okay, it doesn't go through the line more than once, it just touches at one spot. Now, so right here, yes, this is where I stink at drawing this freehand.
Can we grab a ruler?
Sure. We're in the same place as the last 2 years.
Everyone?
So, I'm not crazy about my line. I might try and adjust it a little bit, but nope, definitely don't like that. This- I don't know. You get the idea. Ooh. Okay, I'm keeping that one. I like that one. I drew like half a dozen different ones because, you know, I don't know. I can do it on paper a lot better because I can take the ruler and kind of mess with it. And okay, so unfortunately,
You could just put
it doesn't
two
work
together.
that easily. So, okay, slope of the tangent line. What do I do?
Right.
Rise or run. We know one point this line goes through. So you best be using, what is this, 2, 4? And then I don't know how yours turned out. Mine's almost through this point right here, so I'm going to go with that point. This is an estimate, yes? Because everyone's going to be exact. So mine goes through 5, 6 as another point.
Mine goes to the top one,
Okay.
but I'll just use them.
Yeah,
Well,
I
and
just wrote
it's-
5, 6 and kind of scribbled it around.
This is IROC. This is the slope of the tangent line, right? And whether you use rise over run or y minus y over x minus x, either way, we should be getting, right, I didn't write rise over run on the last one, so I'm going to write rise over run just to have it. 2/3. Okay. So slope of the secant line versus slope of the tangent line. Slope of the secant line is easier in a way because you already know your 2 points. Slope of the tangent line is a little bit trickier because we're not all going to be identical. Okay, for example 2. Have you ever taken a spin class at the gym? Then you know that after the class is over, your rapid heart rate decreases as time passes. As with any physical activity, right? Let's go with this. Have you ever had physical activity? I don't know. Okay. So
That's Mario.
let h of t represent your heart rate. Write an expression. Did you catch that? Write an expression for the rate of change of your heart rate over the period from time t equals 0 seconds to t equals 90 seconds after you have stopped exercising. So we're writing an expression for the rate of change of your heart rate. Thoughts on how to write this?
Something equals h of t.
H of t. In the t, put 90. And then under it, put 90. This is a fraction.
I'm not
Starting in the right
distance,
direction.
That's the thing.
Oh. Just kidding. Doesn't think of that.
I know heart rate is like beats
Beats
per
per
minute
second.
per second.
And notice this is a rate of change. Kind of like average velocity is a rate of change.
But you don't know the distance.
Okay?
It's
So-
like time.
So average rate of change is normally change in distance over change in time, right? But we're not trying to find the change, your velocity. We're not trying to find your average rate of change of velocity. We're trying to find the rate of change of your heart rate. So instead of a change in distance, there's going to be a change in heart rate over change in time. Does that make sense? Now, how do you find the change in heart rate? This is where I said Sophie was starting down the right path, but not there yet.
I
H
just,
of t.
isn't that heart rate?
Right.
Yeah, heart rate is H of t, so, but you would have to put 90.
H of t plus 0.
It's the delta H, change in H.
Change in heart.
So you gotta go H of 0 and H of 90.
Because if we're trying to do the change over a time period,
I omitted that because I thought 0 didn't count.
oh, no. Never assume that 0 doesn't
I
count.
know, because you're going from 90 to 0, so now I was like, okay, it's just 90.
At time
Or from
0,
to 90.
is your heart rate 0?
No, your heart rate
I
should be.
hope.
I hope not, is exactly the answer I'm going to say. So, 0 does matter, you
So
know.
The 0 is like the time. 0 seconds.
Yeah, they gave us the time frame to work with here. which is how I knew to use 0 and 90. Because they said over the period from 0 to 90. Actually, shouldn't it be h of 0? No.
Because then you get a negative. And I hate working on negatives.
Yeah, okay. Either way, it'll work out either way. So h of 90 minus h of 0 over what goes on bottom?
90 minus
90 minus 0. Which I guess is 90, but you're not going to see me just write 90. I'm going to write the 90 minus 0 to make the point.
But that's
that
where
never
I got it,
matters.
because like I did the bottom in my head, and I was like, oh, okay.
And what is my label here?
Beats over second.
Beats per second. They just want an expression, folks. We wrote an expression.
Learn
Yes.
to solve it.
So, if you were to flip the 0 and 90 on top, would you have to do the same thing on bottom?
Yes. Yeah. And as long as you're consistent both places, negatives will work out the same.
So we don't have to solve it.
You just have a negative.
There's nothing we can solve.
Nice.
We don't know what h of t is, so what can I solve?
Oh, okay, that makes sense.
That's why it's called next.
That's why it says write an expression, because there's nothing I can do there.
You're so mean.
Okay. Moving along. A hypercoaster.
That sounds painful.
Is this a new?
So
It's a
book different from last year.
No, this is the same one as last year. So, is a special circuit roller coaster with a height measuring greater than 200 feet. If a new hypercoaster is under design to have its largest drop on the circuit modeled by the equation below, where d of t is measured in feet and time t is measured in seconds. Okay? Find the average speed / velocity of the hypercoaster from 2 to 8 seconds.
Okay,
You just plug in the time.
but
Into
You have to set up two different
what's
equations.
d?
Distance.
Oh wait.
CO2
T is
I think.
My head hurts.
Yeah. But you-
Yes.
And it finds d of t is measured in feet, so that tells you it's the largest drop, so that's your drop in feet that is that representing that d of t.
So we just set two equations, one with 2 seconds, one with 8 seconds, and then
subtract.
I wouldn't think of it as two equations as much as just we're trying to find average speed or velocity. So how do we find average velocity?
plug in
Change of
Distance to time.
over time. So, and if I call it, I'm going to use a rock here, but change in distance. How am I going to show that I'm finding change in distance? Because if you think I'm writing that equation out, you're crazy.
So
dt.
But not t.
D of
S.
8
8.
minus d2.
Over
8 minus 2.
Notice the lovely little calculator symbol,
means you can use your calculator.
pretty much.
They thought I was using my calculator on this.
Are you crazy?
Okay, so
Now.
Is this part where we want to do that trick that you showed us?
yes.
This would be a reason why I showed the trick. Unless you want to plug 8 into this formula, and then 2 into this formula.
Actually, yeah.
Some of you will, and that's fine. I mean,
I did it all of
it
physics
really
last
comes
year.
down to you do you. Okay? That's always going to be my opinion is I'll show you multiple different ways. There is nothing wrong with doing the old school of I'm just going to plug in this, plug in that. I mean, heck, I don't know that it would be a whole lot longer here. Now, here's where will my trick really help is if you have to use this equation 20 different times. Right? If you're using this equation a whole bunch of different times, then you're going to want it plugged in. If you're just using the equation like right here, it wouldn't be horrible. Just plug it in 2 different times. And in fact,
Typing on my calculator again.
Let's just do it a different
Like right there, that's what I get when I plug in 8. Now if I want, I can just change all those 8s to 2s. Do I run the risk of making a mistake here? Oh yeah. So now if I set up my fraction, I do the first one minus the second one over 8 minus 2. Maybe? Is that the answer you guys got? Oh crap, that's not the answer I have written in my notes.
I got
So
63.47.
That's what I got.
that's what I got.
Not quite.
So obviously, I just showed an example of how it's easy to fail. You laugh, but it's true. Yep, and you know what I did? I transposed. I did 20.46 instead of 20.64.
Oh, I
Now,
did the same
here's the
thing.
deal.
No, I didn't.
That could have happened any way I did this.
Right.
I mean, I just transposed those two numbers, so that could have happened anyway I did that. So ignore my answer on the calculator up there because it is wrong. The 63.47 that Doug and Mario mentioned is what I have in my notes. Hopefully some others are getting it as well.
Okay, I'm not. I
put
think
it
I
in
made
my
a mistake
graph
somewhere.
instead of my normal.
Okay.
Is that
I think I made a mistake
I just
somewhere,
went
but
and
I'm not
tried
seeing
it.
it.
Like, I want to try it.
What's my label?
Got it.
per second?
Okay. Now, here's the deal, guys. I just did that the long way and messed it up. And guess what? I have to use the same formula
I got 63.
again. So B, what's the average speed velocity of the hypercoaster from 4 to 6 seconds? What are we doing this time? Same thing, but with D of 6 minus D of 4 over 6 minus 4. This is where I wish I would have just typed it in the first line because that would have saved me.
I used parentheses and I got a different answer.
Mario.
Be quiet.
That looks right. What am I?
I know, I went there too and I can't find it. Because all I
Is
did,
that not
all
what
I
it's
did
supposed to
from
come up
yours
with?
was use the parentheses. That's not what yours was.
Mine's wrong up there.
Oh.
I used 20.646 instead of 20.64.
If I
So-
take these two.
Yeah, so
6, 7, 8.
try those numbers. It's very possibly right. I messed mine up.
Oh, okay.
Deleted all that.
Don't go by your teacher.
Okay.
48.51.
Yes. 48.51.
Crazy.
It worked now?
Yeah.
I did.
Okay.
Now I did that.
What did you get?
I got 470.18. That's what I got.
Oh, because you're. I mean, you got that first part right, yeah. You gotta finish it.
Oh, you're right. Okay.
Now you just gotta plug it forward.
Okay, one of the things we have to get in the habit of doing is we have to be able to write out answers at times. Okay, and not just give a numerical answer. So one of the things, I can use that AROC shorten, but the average rate of change on the interval 4 less than or equal to t less than or equal to 6, I forgot seconds, is about 48.51 feet per second. Man, I'm making a mess of this. C says to estimate the instantaneous speed. I'm thinking I should have just told you guys to type that D in to your equation if you didn't, because now what are we going to have to do on C?
Same thing.
The same formula again.
I did it. I put it in there.
Very proud of myself.
See, I tried to show you that you don't have to, and I messed that up. But my mistake would have been wrong anyway. It doesn't matter what method I used. My mistake would have just gotten me.
So for C, what do you put in the y1? You put 5x squared.
Say what now?
How do we do the trick on this one? Like for this part.
So we're using that formula there. You're using this formula right here.
Okay.
So you would want to type in whether you use y1, y2, whatever. You know, like I can pick y2 this time if I want, but I'm going to type in 1.7 x cubed minus 20 point, what is it? 64 x squared plus 112, 112.79x
Oh my
plus
god.
132.56. And so for me now, that is my y2. You can put it at y1, it doesn't matter. Double check, make sure you typed it right. And then you can just set up a fraction bar here. My alpha F4 will bring up my y2. And it's going to be y2 of, I can't see. Minus y2.
The first one.
For me, I'm using y2. You do you.
Hold on. See? Got 47.3997.
Okay. Never mind.
That.
Oh, I forgot the minus sign.
But if you just forgot the minus sign in your original equation, or did you get it on the
On this.
screen? Okay.
There we go.
You repeat 2 more times, right? Are we okay with what I'm doing here?
I think so.
Most of you guys are writing on your calculators. Writing on your calculators? Oof. Working on your calculators, so.
I really like your trick about copying and pasting and just inserting.
Oh, and then just adjusting your numbers.
Yeah.
Yeah.
I do like that. You just have to be careful, make sure you don't goof it up.
Mm-hmm.
And I know I taught you guys how to use insert last year, right? So you know that, and we can review it, but if you're trying to insert a character, because if you just start typing, it just types over what's there, right?
Mhm.
You need to insert a character, which we often do on these. That's very doable.
I learned this last year in physics, so I was like, I'm not writing out all this stuff again.
No, about 5 minutes ago, I did a mental breakdown, and now I feel okay.
Okay, those are my values. In all reality, those are my values I have written in my notes from last year is what it is, but
I went way farther than you did.
what is there to go farther? Oh, did I round that?
Yeah, because I got like
Okay.
on the second one,
I'll just do like this,
46
it's okay.
714287.
And this is where I did, I looked through the notes this morning. I'm like, okay, I know how to do that. I don't need to recalculate it. Okay, real quick, in our last 3 minutes, and we'll have 1 page left to do tomorrow. I don't know if I'm quite where I need to be or not, but explain the meaning of the instantaneous speed, velocity, in the context of the question at t equals 5 seconds. Okay, guys, very common in calc is that you need to be able to, okay, what does this mean? We have these values, but what does this mean? Okay, if we're looking at our instantaneous speed is about that. Okay, and we can keep going and get more and more specific. Okay, but we have about that. What does that mean?
There you go. About.
That is about what the speed is at exactly 5 seconds.
Well, but this wasn't, what does this equation represent? What is d of t? What was that? If you look back in the context of the problem, that d of t represents the drop,
Drop, yeah.
right?
The largest drop of the surface.
Yeah, so if you go back and that talks about the drop, so the rate of change in the drop of the hypercoaster, at what time are we talking?
5.
5 seconds is about that 46.6474 amount, feet per second. So what I have written here, the rate of change, oops, in the drop of the hypercoaster. Wow, that's not readable. At 5 seconds is about, and I say about because this isn't precise, is it? 46.647 feet per second. Okay, so when they want you to explain the meaning, it's not just, oh, it's 46.647 feet per second. What does it mean? Okay, now, what I'm going to ask you to do, because I'd really like to make sure we are totally finished with 1.1 by the end of tomorrow, in terms of also checking homework. Go through, do the 1.1 homework you can tonight. Does that make sense? Now, are there some things that might be a little fuzzy because we haven't gotten to the last page of notes?
Yes.
Possibly. But in all honesty, you might know how to do most all of it. Okay? So go through, do the homework. We'll start the period by finishing notes, and then we will try to finish the home, have a little time to finish homework and that type of stuff. I do not have the answer keys up in Schoology yet. I haven't decided what I'm going to do about that. I might just wait on the first day. Okay? Have you work out a little bit.
Actually, wait.